Quantum 1, tutorial question number 9. Okay, here we have an electron. It's accelerated through a potential difference of 6.0 kilovolt from rest. Well, whenever we have an electron, let's say initially at rest, how do we give it some speed, some Ke to the electron? How do we accelerate the electron? Well, the standard way is to apply a voltage. Okay, apply a voltage. Then the electron will be accelerated by the voltage. Okay, that's how we accelerate the electron to some speed, some Ke. So once the electron got some speed and some Ke, then they ask us what is the correct de Broglie wavelength of this electron. Okay, what happens that we previously we learned that a light behave like particles. Okay, each particle has energy and momentum. But later on we also learned that electron, which we already know that is a particle, but in some situation the electron can behave like a wave. And a wave, being a wave, it has a wavelength. So this electron basically has transformed into a wave, and now we're going to find the wavelength of this wave. Okay, so the answer is B. Okay, how do we get the answer is B? First of all, the de Broglie wavelength of electron can be found from using this de Broglie formula. The momentum of the electron is related to the wavelength. So if you want to find the wavelength, okay, you just take h over momentum. That will give you the wavelength. Okay, so in order to calculate the wavelength of the electron, you need to calculate the momentum of the electron. Okay, how do we calculate the momentum of the electron? Well, there's basically what we do is the electron's Ke is gained from the loss in electric potential energy. So the first step we will do is we equate the loss in electric potential energy, which is E times V, the voltage, equal to half mv squared. Actually from there you can find the speed of the electron. Then after that you can find the momentum as mv. Then you substitute mv into this p. Then from there you can find the wavelength and then you get the answer. A faster way would be, instead of using half mv squared as the formula for Ke, we can use another formula for Ke, which is p squared over 2m. Okay, p squared over 2m. How do we get half mv squared into p squared over 2m? Basically it's like this. We have half mv squared. Okay, so this can be just using some math trick. What we can do is we can times m on top, so m become m squared. If we times m on top, then of course we will have to divide. We also have times m at the bottom. So half mv squared is the same as half m squared v squared over m. Then m squared v squared is simply momentum squared. So it's half p squared over m. So there are two formulas, two very commonly used formula for Ke. One is half mv squared. And sometimes if you want to find the p straight away, you can use the other formula for Ke, which is half p squared over m. So here if we equate the loss in electric potential energy to Ke, and then we use p squared over 2m, from here we sub in, we can find p straight away. Then after we find p, we sub into here, we can find the lambda straight away. So you sub in, you get lambda equals to 1.6 times 10 to the minus 11 meters. Answer is B. Okay, so that's question number 9.